Welcome to another informative series brought to you by Autruo. The last time, we looked at the programmable logic controller as a whole. The intricate part that made up this device was discussed in detail. Finally, we ended up looking at the programming language that are used during PLC programming. In today's series, we will be looking at input and output modules. The type we have will be discussed in detail, coupled with the practical examples. Stay tuned. Hendrick, Lorra can be of an help here. Let's listen and learn from her.
Perfect, Andrea.
Well, I believe Andrea would have done some justice in some ways. Be it as it may, I/O modules are used in gathering data from the field device, and at the same time, it is used to control field devices. Now these I/O modules come in two forms, which are the normal I/O modules, and the supplicated I/O modules that come with hardware and diagnostic interrupt capabilities. Again, I/O modules come in four forms, which are I/O modules with 8 channels, I/O modules with 16 channels, I/O modules with 32 channels, and I/O modules with 64 channels. All these channels have their unique terminal assignments. Andrea will discuss this in detail. Over to you, Andrea.
Lorra, can you share some light on that supplicated I/O modules? I mean the one that comes with hardware and diagnostic interrupt capabilities.
The major difference between them is the extra LED that comes on when there are issues, which are in the events of short-circuiting and open circuits conditions, and the ability for the module to be programmable via the programmable software, which can either be SIMATIC Step 7 or TIA Portal applications.
No wonder. We sometimes see some red LED flashing when there are issues. Alright, perfect. Fully understood.
Thanks, Lorra. Let's look at a practical example. It is important that we check the part number of the card we are working on. In our case here, we are working with SM321 modules, which is a digital input with 32 channels. Rated 24V DC, with part number 6ES7321-1BL00-0AA0. The card is divided into 4 parts with different terminal assignments. Let's look at the wiring diagram. By wiring terminations, the module is grouped into 2, with 16 channels on both sides. Now, in order to power on the first group of these modules, pins 2, 9, 12, and 19 will be connected to the positive terminal of a 24V DC source, while pin 20 will be connected to a negative source. Like the other group, this group will be connected as follows. Pin 22, 29, 32 and 39 will be connected to the positive terminal of a 24V DC source, while pin 40 will be connected to the negative terminal of the DC source. The remaining slot is for the field device feedback. Now let's look at the terminal assignments because this has a relation with the status display. Again, earlier on, I said the 32 channels are divided into 2 groups with 16 channels. These 2 groups I will be further divided into 2, which means at the end of the day, we are going to be having 4 in total. Now the first set of channels is denoted as X, which means 0, while the second set is denoted X plus 1. You know what that means? That means it is 1, right? The third set is denoted X plus 2, which is 2. And finally, X plus 3, which is also 3. With these, The channel increment can be represented across the set of channels, which are 8 channels in each set. Now, let's make it sync. Because the first set is 0, the 8 channels will be represented as follows: I0.0, I0.1, I0.2, I0.3, I0.4, I0.5, I0.6, and I0.7. Again, it is worth noting that, during channel addressing, the addressing usually starts from 0, not 1. Again, the next set will be I1.0, I1.1, I1.2, I1.3, I1.4, I1.5, I1.6, and I1.7. Let's see if you have fully grasped the concepts. The third set should be.
Okay, yeah. It should be I 2.0, I 2.1, I 2.2, I 2.3, I 2.4, I 2.5, I 2.6, and I 2.7, while the last channel will be I 3.0, I 3.1, I 3.2, I 3.3, I 3.4, I 3.5, I 3.6, and I 3.7.
Perfect. Let's look at how it is usually represented during program writing. That way, it will be fully understood. In this program run, we have 3 sets of input devices. So in the first scenario, we intend to use the first channel only. The first part of the rung, which is sensor 1, is addressed at I0.0. Sensor 2 is addressed at I0.3. And finally, sensor 3 is addressed at I0.7. Now there is a need for us to wire the sensor to the appropriate ports now when the conditions are met. As we can see in the software, the indicator light will also come on for us to see. To make it even sync further, let's terminate the sensor across the other channel. The first sensor will be terminated to I0.4 of the first channel. Another sensor will be terminated to I1.3 of the second channel, while the third sensor will be terminated to the last channel of I3.4. Now when we triggered our input, the indicator's LEDs will come on across the channels. The output module is also similar to the input modules. Just that instead, the assignments pin also give out a positive 24 volts as per program requirements. The terminal assignments are also similar to the input assignments. Just that, X will now be denoted as Q. I think you can fill up this right.
Yeah. The first channel will be Q0.0, Q0.1, Q0.2, Q0.3, Q0.4, Q0.5, Q0.6, and Q0.7. The second channel will also be Q1.0, Q1.1, Q1.2, Q1.3, Q1.4, Q1.5, Q1.6, and Q1.7. The third channel will be Q2.0, Q2.1, Q2.2, Q2.3, Q2.4, Q2.5, Q2.6, and Q2.7. Finally, the fourth channel will be Q3.0, Q3.1, Q3.2, Q3.3, Q3.4, Q3.5, Q3.6, and finally Q3.7. The analog modules, on the other hand, are used for devices that transmit and receive varying currents and voltage. Again, if you might want to learn more of these, you can check one of our series on that.
Now back to the topic. This is a little different here as compared with the digital module, because there is a need for some additional settings which are current and voltage settings. Measuring range, which is 4 to 20 milliamperes, or 15 volts, or 1 to 24 volts. We will start with the voltage measuring analog module. In the module we have here, the pin is connected to a positive voltage terminal of 24 volts, while pins 10, 11 and 20 are all wired to the negative terminal of the 24 volts. For the voltage sending device, which are mostly transmitter and thermocouple, the positive wire will be terminated to pin 2, while the negative wire will be terminated to pin 3. While for the 4-wire transducers, the positive and the negative will be connected to pins 12 and 13. While the transducer itself will be powered with an external 24-volt source. We can go on and on. Overall, all these won't have been possible without the invention of these noble men. Many consider Michael Faraday as the father of electronics, while some consider Sir John Ambrose Fleming as the father of modern-day electronics. Again, this won't have been possible without the introduction of modern-day solid-state switching devices. The advent of Walter Brattain and William Shockley at Bell Labs greatly revolutionized technology as a whole. Now let's do a quick recap. We started off looking at digital I/O modules. The terminations assignments were looked at in detail. Finally, we ended off looking at analog I/O modules. The way this device was wired was discussed in detail. In the coming series, we will be looking at text-based and graphical programming languages. How this language can be used in a programming language will be discussed in detail. Hope you have learned something new today. See you in the next one.